There's something happening right in front of you that your brain refuses to accept. Every second, billions of particles around you are doing something so bizarre, so fundamentally impossible, that if you truly understood it, you'd never look at reality the same way again. Most people will go their entire lives without grasping this one law of nature. Not because they're not smart enough, but because it violates everything we think we know about how the world works. Right now, as you're watching this, particles in your phone screen are existing in multiple states at once. The air molecules around you are behaving like waves and particles simultaneously. The very atoms that make up your body are connected to other atoms across the universe in ways that Einstein called spooky and impossible. Yet here we are, and it's all happening whether you understand it or not. This isn't about some abstract theory that only matters in laboratories. This is about the fundamental nature of reality itself. The law we're about to explore doesn't just govern tiny particles. It shapes everything from how your GPS works to why the sun shines. It's the reason quantum computers will soon crack codes that would take classical computers longer than the age of the universe. And once you see it, really see it, you'll realize that the solid, predictable world you think you live in is actually built on a foundation of pure impossibility. The law has a name. It's called the uncertainty principle. But that name doesn't begin to capture what it really means, because this isn't just about being uncertain. It's about reality itself being fundamentally undetermined until the moment you look. It's about the universe having no fixed script, no predetermined outcomes, no concrete facts waiting to be discovered. Instead, it's about a cosmos where the very act of observation creates the reality you observe. Most people hear about quantum mechanics and think it's just weird science that doesn't affect their daily lives. They imagine it's confined to some distant realm of subatomic particles and laboratory experiments. But that's exactly backwards. Quantum mechanics isn't separate from your everyday experience. It is your everyday experience. The only reason you don't notice it is because your brain has evolved to see patterns, to create the illusion of solid objects and predictable outcomes from what is actually a seething ocean of quantum uncertainty. Every time you flip a light switch, you're harnessing quantum mechanics. The electrons flowing through the wires don't follow neat, predictable paths like marbles rolling down a tube. They exist in probability clouds, tunneling through barriers they shouldn't be able to cross, behaving like waves that interfere with themselves. The light that hits your eyes isn't made of little balls flying through space. It's packets of energy that somehow know whether you're watching them and change their behavior accordingly. This is where most explanations of quantum mechanics go wrong. They start with the math, or they focus on the technology, or they get lost in philosophical debates about what it all means. But the real power of understanding quantum mechanics isn't in memorizing formulas or learning about applications. It's in recognizing that the entire foundation of your perception of reality has been built on assumptions that simply aren't true. You assume that objects have definite positions, that events have specific causes, that information can't travel faster than light, that the past is fixed and the future is open. You assume that observing something doesn't change it, that reality exists independently of whether anyone is looking. These aren't just beliefs. They feel like obvious facts about how the world works. But quantum mechanics reveals that every single one of these assumptions breaks down at the most fundamental level of nature. The uncertainty principle isn't just one discovery among many. It's the key that unlocks everything else. It tells us why particles can be in two places at once, why measuring one particle instantly affects another particle on the other side of the galaxy, why the act of observation determines what you observe. It explains why reality seems solid and predictable on large scales, but becomes fluid and probabilistic when you zoom in close enough. Here's what makes this so difficult to grasp. Your brain didn't evolve to understand quantum mechanics. For millions of years, Our ancestors survived by making quick decisions about medium-sized objects moving at moderate speeds. They needed to know whether that shadow was a predator, whether that branch would hold their weight, whether that rock would hit its target. None of these survival skills required understanding what happens when you try to measure the exact position and momentum of an electron simultaneously. So your neural circuits are hardwired to see the world in terms of definite objects with specific properties. You see a ball as being either here or there, never in multiple locations at once. You experience cause and effect as flowing in one direction through time. You think of observation as a passive activity that reveals pre-existing facts about the world. These mental shortcuts work perfectly for navigating everyday life, but they become obstacles when you try to understand how reality actually operates at its deepest level. The uncertainty principle forces you to abandon these mental shortcuts. It demands that you accept something that feels impossible. When you try to measure certain properties of a quantum system with perfect accuracy, you inevitably disturb other properties. Not because your measuring instruments are clumsy, but because the universe itself places fundamental limits on what can be known simultaneously. Think about what this means. In classical physics, you could imagine measuring the position and speed of a baseball with arbitrary precision, given sensitive enough instruments. You might not be able to do it practically, but there's no theoretical limit. The ball has a definite position and a definite speed, whether you measure them or not. But in quantum mechanics, this logic completely breaks down. An electron doesn't have a definite position and momentum simultaneously. It's not that these properties are hidden from you. It's not that your instruments aren't good enough to detect them. It's that the electron genuinely doesn't have both properties at the same time. The act of measuring its position creates a disturbance that makes its momentum uncertain. The act of measuring its momentum spreads out its position. The more precisely you pin down one property, the more the other property becomes fundamentally unknowable. This isn't a limitation of human knowledge. It's a feature of reality itself. The universe doesn't contain complete information about its own state. Instead, it exists in a constant state of partial determination, with some properties sharp and others fuzzy, and the act of measurement shifting which properties are which. Now, you might be thinking this sounds abstract and removed from anything that matters in your life. But consider this. Every piece of technology you use depends on quantum mechanics working exactly this way. The computer processing this video, the screen displaying it, the internet connection transmitting it, they all rely on quantum effects. The uncertainty principle isn't just a curiosity. It's the foundation that makes the modern world possible. Semiconductors work because electrons can tunnel through barriers they classically shouldn't be able to cross. Lasers work because atoms can emit light in perfectly synchronized ways that classical physics can't explain. MRI machines work because atomic nuclei can be put into quantum superpositions that respond to magnetic fields in precise, predictable patterns. GPS satellites have to account for quantum effects in their atomic clocks to maintain accuracy. But here's where it gets really strange. The uncertainty principle doesn't just apply to position and momentum. It applies to energy and time, to different components of angular momentum, to any pair of properties that are related in specific mathematical ways. The universe seems to be built on a network of trade-offs, where gaining perfect knowledge about one aspect of a system necessarily creates uncertainty in another aspect. This has profound implications for how information works in the quantum world. In classical systems, you can always make a perfect copy of information without disturbing the original. You can photocopy a document, download a file, or memorize a phone number without affecting the source. But quantum information behaves differently. There's a fundamental principle called the no-cloning theorem that says you can't make perfect copies of unknown quantum states. This isn't just a technical limitation. It's a deep statement about the nature of reality. Quantum systems can't be perfectly observed without being disturbed. and they can't be perfectly copied without being destroyed. Information in the quantum world is fragile, unique, and intimately connected to the physical systems that carry it. The more you dig into the uncertainty principle, the more it reveals about the strange architecture of reality. It's not just that we can't measure certain things precisely, it's that the universe itself seems to be constructed in a way that prevents complete knowledge, while still allowing for remarkable precision in the things we can measure. Scientists have spent decades testing the boundaries of the uncertainty principle, trying to find ways around it, looking for loopholes or exceptions. But every experiment confirms it more deeply. The principle isn't just a rule about measurement. It's a statement about the fundamental structure of space, time, matter, and energy. It tells us that the universe is built on a foundation of irreducible uncertainty, and that this uncertainty isn't a bug in the system. It's a feature that makes everything else possible. The uncertainty principle doesn't just tell us what we can't know. It reveals something far more unsettling about the nature of existence itself. When Werner Heisenberg first discovered this principle in 1927, he wasn't just finding a new rule about measurement. He was uncovering a crack in the foundation of reality that would eventually split our understanding of the universe wide open. Picture this scenario. You're trying to look at an electron under the most powerful microscope imaginable. To see something, you need to bounce light off it. But light comes in packets called photons, and when a photon hits an electron, it kicks the electron in an unpredictable direction. The more precisely you want to see where the electron is, the higher energy photons you need to use. But higher energy photons kick the electron harder, making its momentum more uncertain. This isn't a problem with your equipment. This is the universe telling you that there's a fundamental limit to how much you can know. The act of gaining information about position necessarily destroys information about momentum. It's like trying to read a book in a dark room by striking matches. Each match gives you a glimpse of the words, but the light also burns part of the page. The more light you use to you're trying to read, but see clearly, the more you destroy what here's where it gets truly bizarre. The uncertainty principle suggests that particles don't even have definite positions and momenta to begin with. Before you measure an electron, it exists in what physicists call a superposition. It's not that the electron is at some specific location and we just don't know where. It's that the electron genuinely exists in multiple locations simultaneously, with different probabilities for being found in each place. This violates everything your intuition tells you about how objects should behave. If I asked you where your car keys are right now, you'd assume they have a definite location, whether you know it or not. Maybe they're on the kitchen counter, maybe they're in your pocket, but they're somewhere specific. In the quantum world, particles are more like ghosts that haunt multiple locations at once, only materializing in one spot when you force them to by making a measurement. The mathematics of quantum mechanics describes these ghostly states using something called a wave function. Think of it as a probability map that shows where a particle might be found when measured. The wave function can spread out over vast regions of space, meaning the particle has some chance of being detected almost anywhere. But the moment you perform a measurement, something extraordinary happens. The wave function collapses, and the particle suddenly appears at one specific location. This collapse isn't gradual, it's instantaneous and complete. One moment, the particle is spread out like a cloud of possibilities. The next moment, it's localized at a single point. It's as if reality itself is making a decision about what to be. And that decision only gets made when someone or something demands an answer. The implications stretch far beyond individual particles. Consider what happens when particles interact with each other. In the classical world, you might imagine particles as tiny billiard balls bouncing off each other in predictable ways. But in the quantum world, particles can become entangled, meaning their properties become linked in ways that defy explanation. When two particles are entangled, measuring one instantly determines the state of the other, no matter how far apart they are. Einstein hated this idea so much he spent years trying to prove it wrong. He called it spooky action at a distance and argued that it violated the principle that nothing can travel faster than light. But experiment after experiment has confirmed that quantum entanglement is real. This creates a profound puzzle about the nature of information and causality. How can measuring a particle on Earth instantly affect a particle on the other side of the galaxy? The answer seems to be that entangled particles aren't really separate entities. They're part of a single quantum system that transcends ordinary notions of space and distance. The uncertainty principle governs these entangled relationships too. When particles are maximally entangled, they give up their individual identities almost entirely. Neither particle has definite properties on its own. Instead, they share a kind of distributed existence where measuring one reveals information about both, but destroys the entanglement in the process. This leads to one of the most mind-bending consequences of quantum mechanics. Information in the quantum world can't be copied without being destroyed. If you try to read the quantum state of a particle and duplicate it, the original state gets disturbed by the measurement. It's as if the universe has built-in copyright protection for quantum information. This no-cloning principle has enormous practical implications. It's the foundation of quantum cryptography, which promises to make communications absolutely secure. If someone tries to eavesdrop on a quantum message, the act of observing it necessarily changes it, alerting the sender and receiver that their privacy has been compromised. But the strangest part of the uncertainty principle might be how it relates to energy and time. Just as you can't measure position and momentum simultaneously with perfect precision, you can't measure energy and time with perfect precision either. This means that over very short time intervals, the universe can violate conservation of energy, borrowing energy from nowhere and paying it back before anyone notices. This temporal uncertainty allows for what physicists call virtual particles. These are particles that pop into existence from pure vacuum, exist for impossibly brief moments, and then disappear back into nothingness. They're not real in the sense that you could capture one and put it in a jar, but they have measurable effects on the world. They're responsible for forces between particles. They cause empty space to fluctuate with energy, and they might even be related to the mysterious dark energy that's accelerating the expansion of the universe. The vacuum of space, which you might imagine as completely empty, is actually seething with virtual particles constantly appearing and disappearing. The uncertainty principle ensures that perfect emptiness is impossible. Even nothing is something in the quantum world. These virtual particles reveal another layer of the uncertainty principle's significance. The principle doesn't just constrain what we can measure, it actively shapes the structure of reality. The electromagnetic force that holds atoms together is carried by virtual photons. The strong nuclear force that binds protons and neutrons is mediated by virtual gluons. Even gravity, according to some theories, might be carried by virtual gravitons. In other words, the forces that hold the universe together exist because of quantum uncertainty. If the universe were perfectly deterministic, if everything had exact values all the time, the forces between particles couldn't operate. The fuzziness that the uncertainty principle introduces isn't a flaw in nature's design. It's what makes complex structures possible in the first place. This connects to an even deeper mystery about why the universe is capable of supporting complexity at all. In a perfectly certain world, everything would be static and unchanging. In a perfectly random world, nothing stable could ever form. But the uncertainty principle creates a middle ground, where there's enough fuzziness to allow for dynamic interactions, but enough constraint to allow for stable patterns. The atoms in your body are held together by quantum forces that depend on uncertainty. The chemical bonds that make molecules possible require electrons to exist in probability clouds around atomic nuclei. The nuclear reactions that power the sun rely on quantum tunneling, where particles pass through barriers they classically couldn't cross. Even the process of evolution depends on quantum effects in DNA that create the mutations necessary for natural selection to work with. So, when you really understand the uncertainty principle, you realize it's not just about the limits of measurement. It's about why anything exists at all. It's about why the universe is interesting rather than boring, why complexity can emerge from simplicity, why life is possible in a cosmos that could have been either perfectly ordered or completely chaotic. The principle forces us to confront the possibility that reality itself might be fundamentally probabilistic rather than deterministic. Not just because we lack information, but because information itself might be discrete and limited rather than continuous and complete. The universe might be more like a cosmic game of chance where the dice are always rolling, but the rules ensure that some outcomes are more likely than others. This probabilistic nature of reality extends all the way up to the largest scales we can observe. The cosmic microwave background radiation that fills the universe shows tiny fluctuations that appear to be quantum in origin. These fluctuations, magnified by cosmic expansion, became the seeds that grew into galaxies, stars, planets, and eventually life itself. In a very real sense, the uncertainty principle might be responsible for your existence. Without quantum fluctuations in the early universe, matter would have remained perfectly smooth and uniform. No stars would have formed, no planets would have condensed, no chemistry would have been possible. The fuzziness that makes exact measurement impossible also makes complexity and consciousness possible. This brings us to one of the most disturbing implications of the uncertainty principle, something that most people never think about but that keeps physicists awake at night. If reality is fundamentally probabilistic, if the universe makes decisions about what to be only when forced to by measurement, then what happens when no one is looking? Consider a single radioactive atom sitting in a laboratory. Classical physics would say that either it has decayed or it hasn't. There would be some definite moment when the decay occurred, even if no one was there to witness it. But quantum mechanics tells a different story. According to the uncertainty principle, the atom exists in a superposition of decayed and not decayed states until someone measures it. The act of a measurement forces the universe to choose which reality becomes real. This leads to what might be the strangest consequence of quantum uncertainty. The boundaries between what's real and what's possible become blurred beyond recognition. In the quantum world, unmeasured systems don't just have unknown properties. They have indefinite properties. The difference is crucial and deeply unsettling. When you flip a coin and cover it with your hand, the coin has a definite state even though you don't know what it is. It's either heads or tails, and your ignorance doesn't change that fact. But when a quantum system is in superposition, it's genuinely both things at once. A quantum coin would be both heads and tails simultaneously, only choosing one state when you lift your hand to look. This creates a profound puzzle about the role of observers in determining reality. What counts as an observation? Does it require a conscious mind? Or is any interaction with the environment sufficient? If you set up a camera to record the coin flip but never look at the footage, has an observation occurred? What if the camera malfunctions and no record is created? These aren't just philosophical questions. They point to gaps in our understanding that have practical consequences. Quantum computers work by manipulating systems that exist in superposition, performing calculations on all possible inputs simultaneously. But the moment you try to read the answer, the superposition collapses, and you get only one result. The art of quantum computing lies in extracting useful information before the delicate quantum states are destroyed by measurement. The uncertainty principle also reveals something profound about the nature of time itself. In classical physics, time flows smoothly from past to future, with each moment building logically on the last. But quantum mechanics suggests that time might be more like a series of snapshots, with each measurement creating a new frame in the movie of reality. Between measurements, quantum systems evolve according to the Schrödinger equation, which describes how probability waves spread and interfere with each other. But the moment a measurement occurs, the wave function collapses instantaneously, jumping discontinuously from one state to another. This creates a strange dual nature of time, where some processes are smooth and continuous, while others are abrupt and discontinuous. Even stranger, the uncertainty principle suggests that the future might influence the past in ways that classical physics doesn't allow. When you make a quantum measurement, you're not just revealing a pre-existing property, you're participating in the creation of that property. And in some interpretations of quantum mechanics, this creative act can retroactively determine what was true in the past. Consider an experiment where a particle travels from point A to point B through one of two possible paths. In the classical world, the particle would take one path or the other, and evidence of its journey would exist along whichever route it actually travelled. But in the quantum world, the particle can take both paths simultaneously, existing in a superposition of trajectories. Now imagine that you set up detectors along both paths, but you don't turn them on until after the particle has already reached point B. The uncertainty principle suggests that your decision about whether to measure the particle's path can retroactively determine whether it took a definite path route or remained in superposition throughout its journey. This isn't time travel in the science fiction sense. You can't send messages to your past self or change historical events. But it does suggest that the boundary between past and future might be more fluid than we imagine. The act of measurement doesn't just reveal what happened. It helps determine what happened, even if the measurement occurs after the fact. This temporal aspect of quantum uncertainty has led to some of the most mind-bending experiments in physics. Scientists have demonstrated delayed choice experiments where the behavior of particles seems to depend on measurements made after the particles have already been detected. It's as if the universe maintains multiple versions of history simultaneously, only committing to one version when forced to by observation. These experiments force us to reconsider the most basic assumptions about causality and the flow of time. If the present can influence the past, even in subtle quantum ways, then the neat division between cause and effect starts to break down. Events don't just flow forward through time in a simple chain. They form a complex web where future possibilities can reach back to shape past realities. The uncertainty principle also places fundamental limits on computation and information processing. There's a quantum limit to how fast information can be processed, how much information can be stored in a given volume of space, and how precisely information can be copied or transmitted. These limits aren't just engineering challenges. They're built into the fabric of reality itself. This has profound implications for artificial intelligence and the future of computing. As computers become more powerful and approach quantum limits, they'll have to grapple with the same uncertainty that governs the microscopic world. Perfect computation becomes impossible not because of technological limitations, but because perfect information doesn't exist. Even more intriguingly, some scientists speculate that consciousness itself might be a quantum phenomenon. The brain operates through electrical and chemical processes that ultimately depend on the behavior of individual atoms and molecules. If consciousness emerges from quantum processes in neural microtubules or other cellular structures, then the uncertainty principle might place fundamental limits on what minds can know about themselves. This could explain why consciousness seems to have a unified, single-threaded nature, despite being produced by billions of interconnected neurons. Just as quantum measurements collapse superpositions into single outcomes, conscious observation might collapse the multiple parallel processes of the brain into a single stream of experience. The idea remains highly speculative and controversial, but it highlights how the uncertainty principle might extend beyond physics into biology, psychology, and philosophy. If the principle governs not just particles, but also the processes that give rise to thought and awareness, then our very ability to understand reality might be constrained by the same quantum limits that govern the reality we're trying to understand. This creates a strange loop where the observer and the observed are bound together by the same fundamental uncertainty. You can't step outside the quantum world to study it objectively because you are part of the quantum world. Your measurements disturb the systems you're trying to understand, but those disturbances also disturb you in return. The uncertainty principle doesn't just set limits on what you can know about the external world, it sets limits on what you can know about your own knowledge. Self-reference becomes problematic when perfect information is impossible. You can't have complete knowledge of your own mental states any more than you can have complete knowledge of a quantum particle's position and momentum. This might explain why consciousness has such a mysterious, hard-to-pin-down quality. Just as quantum systems resist complete description, conscious experience might resist complete analysis. The act of introspection necessarily changes what you're introspecting about, creating an irreducible uncertainty in self-knowledge. These deep connections between quantum mechanics and consciousness remain largely unexplored, but they suggest that the uncertainty principle might be more than just a law of physics. It might be a fundamental feature of any system complex enough to observe itself. Whether that system is made of quantum particles, biological neurons, or something else entirely, the principle forces us to confront the possibility that uncertainty isn't a temporary limitation to be overcome by better theories and more sophisticated instruments. It might be a permanent feature of existence, woven so deeply into the structure of reality that eliminating it would eliminate everything else as well. The universe might be uncertain, not despite being complex and interesting, but precisely because it's complex and interesting. This uncertainty isn't random chaos, it's structured indeterminacy, with patterns and probabilities that can be predicted even when individual outcomes cannot. The uncertainty principle doesn't say that anything can happen. It says that what happens is constrained by quantum rules that are both more flexible and more rigid than classical laws. Understanding this principle doesn't just change how you think about physics. It changes how you think about knowledge, reality, and your place in the universe. You're not a passive observer of an independent reality. You're an active participant in a cosmic process of measurement and collapse, uncertainty and determination, possibility and actuality. The quantum world operates on principles so alien to our everyday experience that even scientists who work with these phenomena daily struggle to accept their implications. But here's what makes the uncertainty principle truly extraordinary. It doesn't just describe the behavior of isolated particles in laboratory experiments. It reveals that the entire structure of reality is built on a foundation of fundamental indeterminacy that extends into every corner of existence. Consider what happens when you try to measure anything with perfect precision. The very act of measurement requires an interaction between your measuring device and the system you're studying. In the classical world, we imagine this interaction can be made arbitrarily gentle, like carefully nudging a soap bubble to see how it responds without popping it. But quantum mechanics tells us there's a minimum disturbance that can never be eliminated, no matter how sophisticated our instruments become. This isn't a technological problem waiting to be solved. It's a statement about the granular nature of reality itself. Energy, matter, and even grains with sufficient precision to pin down their exact space and time appear to come in discrete chunks, rather than forming smooth, continuous fields. When you try to probe these quantum properties, you inevitably kick them hard enough to scramble the very information you're trying to extract. The mathematics behind this are elegant but unforgiving. The uncertainty principle can be expressed as a simple inequality involving Planck's constant, a number so small that it only becomes relevant at subatomic scales. But within that mathematical relationship lies a truth that reshapes everything we thought we knew about measurement, knowledge, and reality itself. What's particularly unsettling is how this principle scales up into the macroscopic world in unexpected ways. You might think that quantum uncertainty gets washed out when you deal with large numbers of particles, like individual voices disappearing in a crowd. And to some extent, That's true. The chair you're sitting on doesn't suddenly tunnel through the floor because the quantum effects of its trillions of atoms mostly cancel each other out. But the cancellation isn't perfect, and the residual quantum effects accumulate in ways that can have dramatic consequences. The random walk of stock prices, the unpredictable timing of evolutionary mutations, even the chaotic dynamics of weather systems, all contain traces of quantum uncertainty amplified through complex feedback loops. More fundamentally, the uncertainty principle suggests that information itself might have a quantum structure. In classical physics, you could imagine storing infinite amounts of information in arbitrarily small spaces by encoding data in the precise positions and velocities of particles. But quantum mechanics places hard limits on information density, processing speed, and copying fidelity. These limits aren't just theoretical curiosities, they're already showing up in cutting-edge technology. As computer chips shrink toward atomic dimensions, engineers have to grapple with quantum tunneling effects that make electrons behave in increasingly unpredictable ways. The relentless march towards smaller, faster processors is running up against fundamental quantum barriers that no amount of engineering cleverness can overcome. But perhaps the most profound implication of the uncertainty principle is what it says about the nature of physical law itself. Classical physics was built on the assumption that the universe operates like a vast, complicated clockwork. If you could know the exact position and velocity of every particle at some initial moment, you could in principle calculate the entire future history of the universe. The uncertainty principle shatters this deterministic vision. It tells us that the universe doesn't contain enough information to specify its own future completely. Instead of following a single predetermined trajectory through time, reality branches into multiple possibilities at every quantum measurement, with probabilities that can be calculated but outcomes that remain genuinely random. This randomness isn't the result of hidden variables or incomplete knowledge. Decades of increasingly sophisticated experiments have confirmed that quantum indeterminacy is irreducible. The universe really does roll dice, and those dice rolls help determine everything from the structure of atoms to the evolution of galaxies. Even more strangely, the uncertainty principle reveals deep connections between seemingly unrelated aspects of reality. The relationship between position and momentum uncertainty mirrors the relationship between energy and time uncertainty, which in turn connects to the relationship between different components of angular momentum. The universe appears to be constructed from a web of complementary properties that trade off against each other in precise mathematical ways. These trade-offs create a kind of cosmic conservation law for information. You can sharpen your knowledge of one aspect of a system only by blurring your knowledge of complementary aspects. Perfect information about everything becomes impossible, not because of practical limitations, but because the universe itself seems to be designed to prevent complete knowledge. This has led some physicists to speculate that information, rather than matter or energy, might be the most fundamental constituent of reality. In this view, particles, forces, and fields are all emergent properties of underlying information processing systems that operate according to quantum rules. The uncertainty principle would then be a statement about the computational limits built into the fabric of space and time. Such ideas push us toward a radically different conception of existence. Instead of thinking about the universe as a collection of objects moving through empty space, we might need to think of it as a vast information processing system, where quantum computations determine what becomes real from moment to moment. The boundary between physics and computer science becomes increasingly blurred in this picture. Quantum field theories start to look like algorithms for computing the probabilities of different particle interactions. The wave function begins to resemble a cosmic database that stores all possible information about a system while refusing to commit to specific values until forced to by measurement. This computational perspective on quantum mechanics has practical implications that are just beginning to be explored. If the universe really is performing quantum calculations at every scale, then perhaps we can learn to harness these natural computations for our own purposes. Quantum computers represent the first tentative steps in this direction, but they might be just the beginning. Imagine biological systems that have evolved to exploit quantum coherence for energy transport, navigation, or information processing. Some evidence suggests that photosynthesis in plants, magnetic field detection in birds, and even the sense of smell might all depend on quantum effects that remain coherent despite the warm, noisy environment of living cells. If life has indeed learned to work with quantum uncertainty rather than against it, then the uncertainty principle might not be an obstacle to complexity, but rather an essential ingredient. The fuzziness that makes exact prediction impossible might also make adaptation, learning, and evolution possible by creating the flexibility needed for complex systems to explore new possibilities. This connects to one of the deepest puzzles in modern science. How did the universe evolve from simple initial conditions to the rich complexity we see today? Classical physics suggests that entropy should increase monotonically, driving systems toward equilibrium and simplicity. But the universe clearly became more organized over time, not less. Quantum mechanics offers a possible resolution. The uncertainty principle ensures that perfect equilibrium is impossible because quantum systems can never have equilibrium. Quantum fluctuations continue completely definite properties, even in thermal, to create temporary departures from the average state. These fluctuations provide the seed perturbations needed for complex structures to nucleate and grow. The same quantum uncertainty that makes individual measurements unpredictable might also be what makes the universe capable of generating novelty and increasing complexity over cosmic time scales. Without the fundamental indeterminacy built into quantum mechanics, the universe might have remained frozen in its initial configuration forever. This suggests a deep connection between the uncertainty principle and the arrow of time itself. Classical mechanics is time reversible. If you could reverse the velocities of all particles in a classical system, it would retrace its steps back to its initial state. But quantum measurement is irreversible. Once a wave function collapses, you can't uncollapse it and recover the original superposition. So here you are, standing at the edge of a revelation that changes everything. The uncertainty principle isn't just a law of physics. It's the secret architecture of existence itself. Every breath you take, every thought you think, every moment you experience is built on a foundation of quantum indeterminacy that most people will never truly comprehend. But you're different now. You've seen behind the curtain of reality and discovered that the solid, predictable world is actually a shimmering dance of possibilities collapsing into actuality with every passing second. Welcome to the 1% who understand that uncertainty isn't the enemy of knowledge. It's what makes knowledge, consciousness, and existence itself possible.